This talk is about NCT, the Nuclear Compton Telescope, a balloon-borne gamma ray spectrometer, polarimeter, and imager. So here you see the NCT collaboration. It's basically a collaboration between the Space Sciences Lab in Berkeley, the Lawrence Berkeley National Lab, Taiwan, and France. And basically, most of NCT is supported through grants from NASA. And what you see here is basically, this is NCT on its gondola. This here is the launch vehicle. And this is basically NCT shortly before our balloon launch in 2009. So let me start with an overview of the instrument and the campaigns which we had so far. So here you see our detector head, our germanium detector. So NCT is a balloon-borne Compton telescope operating in the energy range from roughly 200 keV up to several MeV, and consists of 12 high-purity germanium double-sided strip detectors with 2 mm of pitch. So those 10 detectors you see here, this was the 2009 balloon flight configuration. We have an energy resolution between 1.5 and 3 keV for width F max. We get a depth resolution of roughly 0.5 mm for width F max, an angular resolution up to 4 degrees, and we have a large field of view. We basically see 1/4 of the sky all the time. Now we had several balloon campaigns so far. We flew a 2 germanium detector prototype in 2005 from Fort Sumner. Then in 2009, this 10 germanium detector prototype flew from Fort Sumner. We had a failed launch attempt from Alice Springs in 2010. And currently we are rebuilding for a new campaign in Antarctica in winter 2014-15, and for 2 more campaigns, 2016 and 2018 from New Zealand. So this is the instrument. What are our science goals? Basically, one of the key science goals is nucleosynthesis, basically unravel the mysteries of how the elements are created and understand the most energetic and violent explosions in the universe. So what we want to do is, we want to map galactic nucleosynthesis, the aluminium-26 line, tracing star-forming regions. Basically here you see the original Compton map of aluminium-26. Want to create an iron map, titanium-44 map. Then we also want to map the galactic positron annihilation, measure gamma ray bursts and their polarization, and observe compact objects and determine their polarization if they have any. So AGNs, black holes, pulsars, and so on. Now here you see the operating principle of our Compton telescope. It's basically the operating principle of a NCT-style Compton telescope, which cannot measure the electron track. So basically you have multiple detectors, and your incoming gamma ray interacts multiple times in these detectors. Then in the beginning you do not know the sequence, but you have to determine the sequence of the interactions by using scatter angle information, absorption probabilities, Klein-Schiene, and so on. But in the end, you are able to reconstruct the paths and reconstruct the origin of the event to an event circle. Now you have an event circle because you missed some information, the direction of the recoil electron. If you would have had the direction of the recoil electron, you could restrict this to a small arc here. But in an NCT case, we just have the event circles here. And basically, the origin of all the photons is where all those event circles overlap. Now, Compton telescopes have come a long way since the first Compton telescope in space, COMTEL. So if you compare COMTEL and NCT, so COMTEL, basically, the distance between the detectors was 1.5 meters, so the whole instrument roughly 2 meters. And NCT, one of those detectors, is 8 centimeters here, so we are much more compact. While COMTEL had a position resolution of roughly 40 square centimeters, NCT now has a position resolution of 1 cubic millimeter. While COMTEL had an energy resolution of roughly 10%, NCT has an energy resolution of 0.2 to 1%. While COMTEL had an efficiency of up to 0.4%, NCT can have an efficiency of up to 16%. And we have a better background rejection, and we can do good polarization. So all in all, we have improved performance with a small fraction of the total mass and volume.
At what energy you have this 16% efficiency?
At roughly, so the peak is roughly 300, 400 kV for Compton events. So here you see our germanium detectors. Here you see one detector where you basically see the strips in one direction on the one side, and it's basically the mirror here, the strips in the other direction. So the size is 8 by 8 centimeters, since they are 1.5 centimeters deep. They have 37 orthogonal strips per side, 2 millimeter strip pitch. They are operated as fully depleted pin junctions, have amorphous germanium and silicon surface layers, have an excellent spectral resolution of 0.2 to 1% for Wave max, an excellent depth resolution, 0.5 millimeter. And for our balloon flights, we have been fabricating 14 of these detectors. 10 have been used for the 2009 balloon flight, and 12 of them will be used for the 2014 campaign. And what you see here is basically the spectra of one of our detectors. It's basically the spectra of each of the interaction point cross sections of the strips. So basically each single pixel. So you basically see we have a very good uniformity, an excellent energy resolution, which is constant. It is very similar over all the detector. And of course, we get good full 3D positioning. Now our germanium detectors are surrounded by a shield in order to veto the dominating atmospheric background component at balloon altitude. So it's basically on the lower hemisphere, it's surrounded by shields. And this is basically one of our shields. The detector is cesium iodide. So for the previous balloon flights, so for the 2005 and 2009 balloon flights, we had a BGO shield, but we now switched to cesium iodide. The size is 48 to 24 by 6 centimeters. The thing weighs roughly 21 kilograms and has a resource threshold of 80 kV.
What was the reason to switch to the...
We just had cesium iodide available. This was just...
Because probably other parameters is not so good. The time resolution or whatever you can get from the anti-coincidence is probably much worse, yeah? Or comparable.
It's not so much worse, no,
not
it's
so
roughly
much.
comparable.
But threshold, probably better for cesium, yeah?
We actually had roughly the same threshold for both, yes. Not much difference. So let's talk about the balloon flights which we had. So this picture basically shows our detector just before launch for the 2005 Fort Sumner prototype flight, which basically had a 2-detector prototype system. And since the 2 detectors were not enough to detect crab, our goal was basically to measure something at floating altitude. And this is what we did. So our flight was for 6 hours on June 1st, 2005. And what we basically measured was the background at balloon altitudes. And what you see here is a comparison between measurements and simulations. So black, our measurements. You see here the strong 511 positron annihilation line in the atmosphere. And basically those colors here are basically the different components which contribute to our background. So the highest contribution is, of course, from atmospheric photons, but you see also the activation lines from neutrons and protons and so on. So all in all, we were roughly within a factor of 2 between simulations and measurements.
Question to this. Here you have at the lower energies over-predicted the background. What have been what kind of software was used? MGG-Pod?
This at 2005 we used MGG-Pod for the simulations.
Okay.
But the over-prediction is probably not MGG-Pod is the reason, but you have to input all the different spectra. And it's always hard to determine all the spectra.
But it's very nice that the higher energy part was quite nicely coincident, more or less. Mm-hmm.
So after the prototype flight, we prepared with a larger instrument for another flight in 2009, again from Fort Sumner. And now the goal is to verify the detection principle in the space radiation environment by detecting the crab pulsar. This is now in detail how the instrument looked like. Basically, here is a germanium detector, which is here in the cryostat here, surrounded by, at that time, the BGO shield, where you see the PMTs here. It all sits in a massive cradle, and here is the liquid nitrogen dewar for cooling. Here's a sun shield surrounding everything. Here you see the whole thing integrated into the gondola. Here's the cradle again with our detectors. This back here is the electronics bay, where all our elite readout electronics, the flight computer, and so on is in. Here is the solar panels. This up here is the differential GPS, which gives us position and orientations. And here is a rotor, which makes sure that we are pointing towards the sun and can charge the solar panels. And down here is the CSBF electronics. Now this is shortly before launch. You see here NCT on the launch vehicle. And now they have installed the crash pads and some ballast here, which we need to keep at a constant altitude. Here in the distance you see NCT, and this basically is all of our balloon here. Here's the helium truck, and it's basically the time where the balloon is going to be filled with helium. This is the moment of launch. And now, and if you look closely here, we came by very closely to Roswell. And this is going to happen when you come close by Roswell. UFO sighted, UFO reported in Arizona and New Mexico, but fortunately NASA gave out a press release soon after this, and basically it says, experts says that the UFO spotted over Arizona was a research balloon launched by the US Space Agency to measure gamma ray emissions.
Sounds so fake. I always say.
So then unfortunately the alien invasion bubble burst. So this is the status after landing. So basically we came down very nicely, landed very nicely, and our crash pads did not roll over. So everything, so the cryostat was completely okay, the detectors remained cooled. So we had some damage to the gondola, but this is always expected, and you see here some damage to the solar cells. But everything was easily repairable, and within a few months we were ready for our next balloon flight. But before this, so this is our, where we are on the way home with the gondola up here. So in summary, we had 22 hours of good flight data and qualified for a long duration balloon flight.
What has happened to orientation system? Was it also intact, more or less?
See,
But just azimuthal orientation?
so the rotor, yeah. So we had some problems during flight with the rotor, but we have a large field of view, so it doesn't really matter where we are pointing.
Landing was a problem or not?
With the rotor.
It survived. Landing.
I think so, yeah.
It's a bit strange.
Why? So the rotor up there. Why should?
But there's some fine mechanic.
Okay. So I don't know the details because this was the CSBF stuff and not our detector, not our stuff. So okay, before we head to the next balloon flight, we now have to analyze our balloon flight data. So the tool which we are using is MegaLib, the Medium Energy Gamma Ray Astronomy Library. And it basically provides simulation, calibration, and data analysis tools for hard X-rays and soft to medium energy gamma ray detectors, cameras, and telescopes. And basically, its name, MegaLib, derives from the Mega detector, which was built at MPE in Garching. But since at that time we always try to explore different options, MegaLib was designed very flexibly, and it can easily be applied to different projects and missions. So MegaLib was used for Mega, ACT, NCT. We used it for COMTEL, GRI, GRIPS, for New Star background simulations, Astro H, Hemi. There's this small detector here, which is a combined Compton telescope and codisk mask for homeland security applications, Dual. Somebody used it for hadron therapy simulations, for X-ray detectors, and so on. And basically, this is this website, megalibtoolkit.com. This is basically the data analysis pipeline. You start out with data acquisition and storage. Then you have to do calibration, which in the NCT case includes energy calibration, including charge loss, charge sharing, and so on, strip pairing, depth calibration. Then you have to do event reconstruction, meaning you have to determine the sequence of the hits in the detector, and basically determine the paths of the photon, and determine a quality factor, how good the event was. Then you have to do event selections, and finally you have to do image reconstruction. So the analysis of Compton telescope data is not very easy. You have lots of steps, and many things can go wrong, and you have to take many things into account. So the first step is energy calibration. So in our case, basically, it includes that we have to take into account the charge sharing between strips. Then we have charge loss between the strips, which we have to correct for, and we also have crosstalk between the strips. Now, when the energy calibration is done, you have to take care of strip pairing. And basically, if more than one interaction happens in the detector, you have to figure out which of the interaction positions are correct. And in this case, it's very easy if you have just two interactions, because usually you have different energies. But it's even more complicated if you have three interactions or single strips on one side and so on. Then another challenge is the depth calibration. And we're basically doing depth calibration by considering the different charge collection time which it takes for the electrons and holes to be collected. So for example here, if you have an interaction near the cathode, then you first collect the holes, and it takes some time until until the electrons have drifted to the anode and until they are collected. So if the interaction is at the center, you basically get the signals at the same time, and if the interaction is near the anode, you get first the electrons and then the holes. And basically from the drift time here, drift time difference, you basically can get the depth. Now when the calibration is done, we have to do event reconstruction. So when we start out, we just have a set of hits in the detectors. And since the interactions are very close by, we cannot get timing accurately enough to use timing to differentiate, to get the sequence. But we have to use other means. And this is called event reconstruction, basically reconstructing the paths of the original photon, then finding the parameters of the original Compton interaction, and basically get a quality factor at the end, which determines how good the event is, or if it originated from incomplete absorption, from some other particle interaction, from charged particle interaction, and so on. So how can we do this? So basically here you see the paths of the photon. Basically incoming direction, this direction, and this direction. And the basic data you have is basically you have this position energy, you have this position energy, and you have this position energy. But since you know we have Compton interactions, we can calculate enhanced information. So one important information here is this Compton scatter angle phi here. This is the Compton scatter angle, and you can calculate this Compton scatter angle via geometry. You know this direction and this direction, then you can calculate this angle. But you also can calculate it from the Compton kinematics if you assume that those two positions came from Compton scattering. So you basically have redundant information. And for the correct sequence, the angle calculated via geometry and via kinematics should be identical. And for all the other sequences, so should not be identical. And what you also can use are absorption probabilities along the paths here. Basically, the probabilities that you have Compton interactions after this distance. If you have complete absorption after this distance, then you can use the Klein-Yeşilin scatter probabilities at this position and this position here. And of course, the probabilities at the above are measured with the current geometry. And in general, there are three basic principles to determine the sequence. A classic Compton sequence reconstruction approach, a Bayesian approach, and neural networks. And basically for NCT, when we have high background conditions and when we also want to identify if the event came from a good photon or from some background event, the best approach to use is the Bayesian approach. Now we have our sequences, and now we have to start to do imaging. So what you see here are basically just back projected event circles. So after the event reconstruction, we know the Compton interaction and basically can each event back project on the sky. Each Compton circle back project on the sky. And here on the left, if we do this with all the data, which was taken while CREP was up, then you see this image here. And basically what you see here, we're basically dominated by atmospheric background. Now, we have to do event selections which get rid of the background. And here's basically the image taken with optimized event selections. And basically what we did is a cut on energy, a cut on the Earth's horizon distance to get rid of most of the atmospheric photons, a cut on the event reconstruction quality factor, and a cut on the Compton scatter angle. And now you basically see that we are dominated by emissions from above. But of course at the cost of a reduced effective area.
Andreas, time cut you're taking just for it?
Just while the CREP, yeah, basically just while the CREP was at least 40 degrees above the horizon. Now the next step is image reconstruction. So basically the imaging process is we have a sky distribution, folded with a detector response, add some background, and we get some measured data. And now we have to do deconvolutions, basically undoing the measurement process. And this is in our case not very easy because we just measure a few events here, and basically and therefore we don't have a unique solution for recovering the sky distribution. So what we can do are iterative approaches. So maximum likelihood, maximum entropy, multi-resolution, stochastic origin ensembles, and so on. And what works best for NCT, in our case here, is maximum likelihood expectation maximization. And what this does is basically goes from this case, we have just the overlapping Compton cones, to really revealing the source here. And if you do this to the data, then we finally get our image of the CREP pulsar. So this is basically the data is the 7 hours at floating altitude while CREP was in the field of view. The energy cut is using energies between 250 kV and 1.5 MeV, where we exclude the 511 background line. We make an event selections on the Earth's horizon cut, Bayesian quality factor cut, Compton scatter angle cut. And then we nicely see CREP. And the detection is basically a 6 sigma detection.
It's clear, much better than was made by Claire.
Yes. So this is basically the first measurement of CREP with a Compton telescope after COMTEL. Okay, now that everything works, we are ready for a much larger balloon flight. From Alice Springs and the southern hemisphere, this would be ideally suited to observe the galactic center region. And basically, our primary goal was basically to map the galactic positron annihilation line as well as the aluminium-26 emission. But unfortunately, we had a launch mishap. And basically, here you see what happened. We had a crash. Basically, see here our electronics boxes scattered around and so on. What happened was the CSBF gondola release mechanism failed on launch, resulting in a crash. But fortunately, the detectors and the electronics chains were relatively unharmed. So, well, we are unlucky and lucky. So now we have to rebuild, and that's what we have done in the last years. So one of the key changes was we're using a new lightweight gondola, which is basically just roughly 1 ton, everything together, and enables ultra-long duration balloon flights. And basically here you see our detector, gondola, electronics compartment, solar shields, and up here is all the communications, basically TDRS communications, iridium communications, differential GPS, and so on. So the next changes is in the old system we had a BGO shield and we now switched to cesium iodide, which also allows us much more space available for our detectors. And we can do an improved geometry, basically a 2x2x3 geometry, which gives us an improved field of view, a better low energy response, and better polarimetry. And you see here, we switched to cryocooling instead of liquid nitrogen cooling. And this also enables long and ultra long duration balloon flights. Now this is a goal for our next campaign. This is the 2014-2015 Antarctica campaign, which should happen in December 2014 until January 2015. And the main technical goal is a long duration test of the new upgraded system and of our real-time analysis for gamma ray bursts, for examples. And basically we will launch here at McMurdo Station, and hopefully we circle a few times here around the South Pole, and then land somewhere close again to McMurdo Station. And the main science goals are gamma ray burst polarization and nuclear line science in the Carina region. Here you see the observable sources during our Antarctica campaign, and you basically see this is the elevation above ground, and 90 degrees means it would go through the zenith. And basically we can see the Large Magellanic Cloud, the Carina region, Vela, Xena, and so on. But unfortunately there are not very much strong gamma ray sources in this region. So that's why our main goal is nuclear line science from the Carina region and gamma ray bursts.
So basically aluminum line probably.
Yes, for the aluminum line. After Antarctica, our plan is to do 2 ultra-long duration balloon flights with a superpressure balloon, 2016 and 2018 from New Zealand. And we basically would launch from Wanaka, New Zealand, go a few times around the world, and then hopefully land safely somewhere in South America. And there the main science goals are nuclear line science in the galactic center region and gamma ray burst polarization again. So this is what we are going to see there. Basically, we would see the galactic center, the Carina region again, and the Vela region, where we could do a nuclear line science. We would see Xena, Large Magellanic Cloud again, and so on.
But Orion is pretty low, yeah?
Orion is pretty low, yeah. So Orion is too low. So basically our effective area is basically constant from 90 to roughly 50 degrees, and then it starts to drop between 50 and 30 degrees to 0. So yeah, everything above 50 is okay, but everything below 0 is. Now let's talk about gamma ray burst science. What you see here is basically the key figure which tells you how good NCT will be doing gamma ray burst polarization. What you see here is the 3 sigma minimal detectable polarization as a function of the fluence and the burst duration. Basically, you see the fluence between 100 keV and 10 MeV, and the red lines are our 3 sigma minimal detectable polarization for a 100-second burst, for a 10-second burst, and for a 1-second burst. And basically, here are 2 observed bursts. Here is the measurement of gamma ray burst 04, 12, 19 with the polarization uncertainty. And if we do a simulation with NCT of this burst and assume 60% linear polarization, we basically measure this modulation signature. And we basically could get the polarization down to a few % accuracy. Yeah, so basically the gray line here is we expect to observe at least 1 burst per 100 days of this strength here, and at least 1 burst per 13 days, which is, has this strength here, and at least 1 burst per 3 days, which is stronger than this here. And this basically tells us that NCT should be able to get good polarization measurements of several gamma ray bursts during the 200-day mission. So now our other important goal is nuclear line science. And basically what you see here is the 3 sigma narrow line sensitivity. So the red band here is the NCT 200-day survey. This band here is the Compton 9-year galactic plane survey. And this here is B1 pointing in 1 megasecond. And you basically see that the NCT 200-day survey will be better than what Compton did in 9 years. So,
sorry, just short comment.
yes.
For SPI, this sensitivity not very simple. They do not see Casey even 6 million combined seconds.
So this is what they claim. So so they do see Cascade.
Yeah,
but this is what they claim. Yes, it's what they claim.
Yeah. So this line of sensitivities probably has to be corrected.
Okay. But I think it's very close to what they claim.
Not for very many lines. For lines, sensitivity which are measured, it's not correct.
Okay, good. So you mean it's higher?
Yeah.
Okay, good. Good.
Yeah. So you're much more sensitive comparatively to speed.
Okay. Okay, but what you see, but of course, what you see here, you should be able to get a better aluminum 26 line map than what Compton did. If you're lucky, we can also do some iron lines here and some iron map. We definitely should see some titanium 44 sources. And if you're lucky, if you get a supernova 1A within, let's say, 20 megaparsec, then we also should be able to see the cobalt 56 line.
Have you calculated probability of observing type 1A?
No, I did not.
200 days flight?
I did not. No, we did not. So this is basically a simulation of the aluminum science, which we can do. So in the background, you basically see here the Compton aluminum 26 map from Plüschke et al. And the foreground are NCT simulations using different aluminum 26 tracer maps between which Compton couldn't distinguish. So on top here is the Derbe 240 micrometer map tracing dust. And this is based on the 53 GHz free emission tracing ionized matter. And basically, Compton should be able to distinguish between those two tracers. And plus, if we are able to do also iron, we basically could also make an iron map and determine if the aluminum emission and the iron emission are similar. So here you see the continuum sensitivity. Again, here is Compton 5 years and NCT 200-day survey. And you see also NCT is not designed for continuum science. You're not so far away from what Compton did. And here is a general polarization performance. Again, you see here the C3 sigma minimal detectable polarization. And as a function of the source flux from 200 keV to 600 keV expressed in Krabs. And basically, orange here is measured polarizations from Krab and Cygnus X1. And those are two sources which we expect to see during our New Zealand campaigns, XNA and the other source here. And blue are basically estimated polarization levels. And you see that NCT should be able to at least give good results on the polarization of those sources. So the detector development is, of course, not over. So the key thing which limits our angular resolution is the strip pitch of 2 millimeters. This basically is the limit of our angular resolution. And if we want to get better, we have to increase the number of, makes the strips smaller. And GRIPS is an NCT-like system for solar observations, which we also are developing at the Space Sciences Lab, and basically uses the same germanium detectors now with 0.5 millimeter strip pitch. And 0.5 millimeter strip pitch basically gives you better interaction resolution, better event reconstruction resolution, better background rejection, and your angular resolution would be roughly 1.6 degrees at roughly 2 MeV. So you will end up with significantly improved sensitivity. And another detector development which we are following is currently we have discrete readout, but GRIPS has switched to ASIC readout, which means lower power consumption, lower mass, and enables the more channels which GRIPS will have. The ultimate goal, of course, is a space mission. And if you compare it to our balloon mission, it has several advantages. You have no atmospheric absorption. You have less background. You need less event cuts and thus have basically more effective area. You have a larger field of view. If you would put NCT at L2 and would use a boom to put it away from the spacecraft, you basically would get a field of view of 4 pi and basically monitor all the sky all the time. And you would, of course, have a longer mission, hopefully. And basically here you basically see the advantages. If you put NCT in a low Earth orbit compared to SPI and COMTEL, basically because we have a much larger field of view, our grasp, which is effective area times the radian, is much larger than SPI and COMTEL. And basically, we would get much more statistics on the sources. Okay, thank you very much.